Welcome. In this lecture, I want to talk about the water cycle. Now, plate tectonics gave us continents, and it shaped and altered them from all the different plate interactions. But plate tectonics actually has very little to do with what the surfaces of our continents look like. That's really the role of water, the water cycle, and behind it, the power of the sun. And this is a really important theme of the entire course and the history of our planet. Our surface is a battlefield between two powerful heat engines, the interior heat engine of radioactivity and the flow of heat out of the Earth, and the exterior heat engine, the light from the sun, driving the rock cycle and water cycle at the surface. Now, it's interesting. The surface runs deep here. Turns out water extends throughout the Earth and plays important roles not just right at the surface. And water is involved with several important themes. They're going to run throughout the rest of this course. One is the remarkable properties of water. It's not a coincidence that geology and biology are both dependent so heavily upon water. Another important theme is just the incredible amount of energy that is supplied by the sun to power the water cycle. And in return, in the process, the incredible, intricate interconnection between the water cycle and the rock cycle. The processes of erosion, transportation, and deposition of rock all have water as their foundation. Now, there are three ways to look at the water cycle, also known as the hydrologic cycle. These are the reservoirs in which water is stored, the residence times for water in the different reservoirs, and the pathways between them. When I say reservoirs, I'm not talking about human reservoirs. I mean the different systems in which water exists: oceans, glaciers, groundwater, lakes, streams, the atmosphere, and the biosphere. And by residence time, I mean how much time on average does any particular molecule of H2O, of water, spend within one of these reservoirs before it follows a pathway out of that reservoir into another. Now, as you probably know, the ocean is really the foundation for our whole system of water at Earth's surface. 97.2% of the water at Earth's surface resides within the ocean. And you have a process within the water cycle of evaporation at the surface of the ocean, carrying water vapor onto land where it precipitates out as rain or snow, and then it runs across the land as glaciers or as streams or under the surface of the land as groundwater, eventually flowing back into the ocean again. That's the cycle. Now, it's interesting that though all of these different reservoirs play important roles, the amount of water that actually exists with them is incredibly variable and quite surprising. Let me try to use this fish tank as an example. Okay, if this tank of water represents the ocean, 97.2% of the water in the surface water cycle, how much actually exists in the other reservoirs? Well, let me try to give you a practical sense. Okay, glaciers are 2.1%, most of the water that isn't in ocean. So glaciers, 2.1% of the total amount of water that exists in the water cycle. If your ocean is this fish tank, that corresponds to about 3 cups of ice. That's our glaciers. Most of the water left over turns out to actually be not on the surface of the land, but in the ground. That's our groundwater, 0.65% of the total, or 2/3 of 1% of the total water. So that turns out, in the case of the fish tank, to be about a cup. So here we have the groundwater, 1 cup's worth. It turns out that the amount of water that exists in lakes is only 0.017% of the total water cycle. This turns out to be about 1 teaspoon's worth. So this water here, 1 teaspoon represents all the water that exists in all the lakes across the surface of the land. Now, the amount in the streams turns out to be even less. It's 0.001% of the total water. And if this is our ocean, that corresponds to about 1/8 of a teaspoon of water. So it's the smallest measurement that I can make here with these spoons. It's a tiny amount trickling down across the surface of the land. That's the streams. And the atmosphere, through which all of the water has to flow before it rains down upon the land, is equal to 0.001%. There's one more important reservoir, and that's the biosphere. And the biosphere is such an insignificant amount of water that I can't even represent it. You wouldn't even be able to see it. And yet, of course, the ironic thing is the biosphere, which contains humans, is one of the most active geologic agents. Now, water is remarkable for a variety of different reasons. First of all, the water molecule, H2O, is not symmetrical. It's got an electrically polar structure. In other words, the 2 hydrogen atoms hang off the oxygen atom at an angle. So there's a positive and a negative polar side to the molecule. And this turns out to be very important because the water ends up able to dissolve other materials. So if you look at the composition of water, it's not just water. It's H2O with all sorts of other stuff in it. And this is called a solution. It's water with all sorts of other minerals dissolved within it. And this is the foundation for geochemistry, and it's also the foundation for biochemistry, for all of life. For instance, taste your tears or blood. What do they taste like? They're salty. That salt water is just like the salt water of the ocean. And that salt water forms the foundation of all of the biochemistry on the surface of our planet. Now, water is interesting for other reasons as well. It happens to have a very high heat capacity. What do I mean by this? It takes a lot of energy in order to raise the temperature of water even a small amount. And the result is water provides a tremendous amount of thermal stability to environments. You probably have a sense of this. Where would you expect temperatures to vary most over the course of a year? Somewhere on the inside of a continent or somewhere along the ocean? Well, it turns out, of course, that the temperature varies much more inside a continent because you're far from the thermally insulating effects of the ocean. I looked up some numbers to give you an example. Fargo, North Dakota, in the middle of January, has a monthly mean temperature of 6.8 degrees. It's pretty cold. But in July, it has a monthly mean, an annual mean temperature of 70.6 degrees. That's a difference of 64 degrees. But if you go to Hilo, Hawaii, the mean temperature in January is 71.4 degrees, and the mean temperature in July is 75.9 degrees. That's a difference of only 4.5 degrees. Why? Because Hawaii is in the middle of the Pacific Ocean, and the ocean just doesn't change temperature very quickly. You need a lot of energy to change the temperature of water even a small amount. And even more importantly, you need a tremendous amount of energy to get it to change its phase. In other words, you need 100 calories to raise 1 gram of water from 0 degrees to 100 degrees Celsius at standard pressure. That's the definition of a calorie. However, you need almost the same amount, 80 calories, in order to melt 1 gram of water from 0 degrees frozen to 0 degrees melted. And it turns out once you get water to the boiling point, it takes 540 calories to boil off that water. In other words, it takes more than 5 times as much energy to boil water as it does to bring water, to heat it from 0 degrees, the freezing point, all the way up to the boiling point. No wonder it takes so long to boil water. It takes a tremendous amount of energy but in the process it provides a tremendous amount of environmental stability. Water has another unusual characteristic in that it expands when it freezes. It's one of the few materials that we know of that does this. Now, this is often very confusing for students because we've just gone through the whole process of volcanoes and melting rock. And rock, like most materials, when you go from a solid to a liquid, when you melt it, it expands. But water just does just the opposite. When water goes from a liquid to a solid, it expands. Just the opposite of what happens with rock. Now, this turns out to be very fortunate for life in streams and lakes because when water freezes, it becomes more buoyant by about 9%, and it floats to the top, forming a layer of ice on top of lakes that insulates the whole rest of the lake underneath, allowing life to continue under the surface during the cold of winter. For geology, this has a vitally important role because when that water gets inside rock and soil and freezes during the winter or at cold temperatures during the night, it expands. And that process of expansion we call frost wedging, and it is one of the most powerful agents of erosion and one of the largest reasons that mountains get torn down so quickly. Now, the start of the hydrologic cycle really begins with evaporation because if you don't have rain, you don't have any water on land, and you need to get water up into the atmosphere first. And that happens because electromagnetic radiation from the sun, primarily in the form of visible light and ultraviolet radiation, hits the surface of the water. Now, remember I talked about the liquid phase of water as being sort of wishy-washy atoms. They keep forming weak bonds with other molecules and then transferring those weak bonds continuously, but still staying loosely bonded. Well, when they absorb ultraviolet radiation from the sun, they get enough energy to break those bonds, and that then isolates an individual molecule which flies off the surface. Now, it doesn't happen often. You need a lot of energy. Remember that high heat of vaporization, of boiling, requires 540 calories per gram. That's good, otherwise the oceans would just be boiling away. But the oceans lose a small amount, but that's enough to keep supplying water up into our atmosphere. The liquid turns into a gas, and it occurs one atom at a time. Now, the sun also drives the thermal convection in our atmosphere, and that's important because otherwise the water vapor wouldn't go anywhere. And what happens is the heat from the sun drives the convection that carries that water vapor over land. Now, evaporation, therefore, happens most rapidly at the equator because you have more direct sunlight. And even though there's not very much water in the atmosphere at any given point, remember, it was that one single drop. You have all the water of the water cycle having to flow through it. And it does this because it has a very fast residence time. Water spends less than a day on average in the atmosphere before it precipitates back out again. In other words, each day the equivalent of a layer of water just 2.5 centimeters thick evaporates into the atmosphere and precipitates out. But that amount of water over time is enough to power the entire hydrologic cycle. Now, I'll talk later on in lecture 30 about the unusual patterns of atmospheric circulation. Once you get that water into the atmosphere, the sun drives a whole set of cycles moving that water about. And there are other factors as well. The rotation of the Earth causes spiraling cyclonic patterns of atmospheric flow. The exact shapes and distributions of the continents and the oceans play a very important role. And indeed, the patterns of ocean currents also greatly affect that atmospheric flow. The result is, however, that water eventually gets carried over continents. And the water very quickly condenses and precipitates. Condensation is a process where the water vapor begins to form very tiny water drops, usually nucleating around something like a dust or salt. These water drops become larger until they become too heavy and they fall out as precipitation. Now, evaporation is highest at the equator, and so is precipitation. For instance, picture yourself in the tropics or a movie that takes place in a tropical jungle. What do you picture? It's probably raining in your picture because it just rains a lot here. There's a huge amount of evaporation and a huge amount of precipitation. And it actually turns out that most of the rain that most of the water that comes up, evaporates up at the equators, falls right back into the oceans, about 90%. Only 10% of precipitation actually happens to occur on land. And of that water that falls on land, in fact, most of it, 75%, gets returned right back into the atmosphere. And it happens through two different mechanisms, either through evaporation from the land or through transpiration, which is a process where water gets absorbed into the roots of a plant, carried through the plant, and then transpired out of the leaves of the plant. So, of the precipitation that happens on land that's not re-evaporated, it turns out very little actually goes into streams and glaciers. Most of that water, 90%, goes into the groundwater. And the rest, only 2.5% of all the precipitation on land goes into streams and glaciers. But they do a tremendous amount of work on the land with that small amount of water that they're supplied with. And this is one of these important themes that I talked about at the beginning of the lecture that I'll come back to. There's just an enormous amount of energy in the whole hydrologic and atmospheric systems. Wind turbines, hydroelectric dams that we install tap only the tiniest amount of this energy. Compared to the global human use of energy, the sun provides a nearly unlimited amount of energy. And I'll talk later on in lecture 45 about solar power, hydroelectric, wind, biomass, the different ways that we can actually tap into this incredible source of energy from the sun. Now, we can actually compute the amount of work water does on land in terms of the amount of energy it actually expends. Turns out about 400,000 cubic kilometers of water evaporates into the atmosphere each year. This is a cube of water about 75 kilometers on a side. Okay? This is a tremendous amount of work that sunlight has to do in order to provide the gravitational potential energy to lift this water up off of the ocean seafloor and lift it in the atmosphere. Imagine lifting a cube of water 75 kilometers on a side. That's 50 miles on a side. Now, once that water's on land, which has a mean elevation of about 875 meters, a little bit less than a kilometer, that water flows down and converts the gravitational potential energy into the kinetic energy of flowing rivers, and then eventually into the energy of work, the friction, the work that water does shaping the Earth's surface. It turns out that amount of energy is equivalent to 2.5 times 10 to the 20 joules per year. Now, a joule, that's our standard unit of energy. And to give you some comparison, 1 joule is the amount of energy it would take to raise something small, let's say a plum, 1 meter up into the air. So 2.5 times 10 to the 20 joules per year is the same as 250 billion joules, or 250 billion plums, all lifted 1 meter up into the air. It's the equivalent of a 1 kilometer high waterfall with about 50 Mississippi rivers flowing over it. Now, if we move through our systems, let's talk about glaciers for a moment. It turns out that glaciers have a volume of, as I said, just 2.1% of the total. But that's 80% of all the fresh water, the water that's not salty seawater. And most of the glaciers are currently located on Greenland and Antarctica. But it turns out that the reservoir of glacial ice fluctuates most of all the different systems. During warm times, there are no glaciers at all. There's no ice stored up on land. During cold times, there's a tremendous amount. And what this does is it drives the sea levels up and down, which turns out to be incredibly important for geology. I mean, if the glaciers melted entirely now, global sea level would rise about 70 meters. That's about 230 feet. Well, that doesn't sound like a lot, but that would put the mouth of the Mississippi River near Illinois. I mean, thank goodness my university in St. Louis is at 450 feet. We'll be pretty close to being beachfront property. During recent ice ages, when there was so much ice on land, global sea level was about 120 meters lower. Just 20,000 years ago, the sea level was almost 400 feet lower than it is today. Now, the system of groundwater has most of the water that's fresh water that's not in the glaciers. It's only 2/3 of 1% of the total, but it's most of the water that's in a liquid form on land. And the groundwater is actually contained within the tiny pore spaces of rock and soil. A very, very small amount of this is in the soil itself, right near the surface. And it's usually either percolating down to the larger groundwater table or it's absorbed by plants. Most of the groundwater actually exists within the rock of the crust itself, either absorbed within the minerals or existing along the boundaries between the mineral grains. The residence time for water in the ground is much longer than for the atmosphere or streams. It can be months if it's in the soil, but it can be hundreds to thousands of years if it gets down into the rock of the crust. Lakes, in comparison, have such a tiny amount of water, 0.017% of the total water. But it's interesting, it's half distributed between freshwater lakes and half as saline basins, salty basins. The freshwater lakes will eventually drain back to the ocean, and the saline basins don't. They lose their water either to the ground or back to the atmosphere through evaporation. Let me give you an example of saline basins. I've talked about that already. Remember when I talked about how the Dead Sea in Israel formed by the pulling apart of a basin along the Dead Sea Transform Fault? Well, the water that flows into the Dead Sea never flows back to the ocean. It just evaporates, making the Dead Sea become incredibly salty. The Caspian Sea is actually the largest saline basin. Utah's Great Salt Lake is another good example. And the reason that the basins get so salty is that, now remember, water isn't just water. It's H2O, it's hydrogen and oxygen with a lot of other stuff dissolved in it. And the water contains these dissolved salts and rocks. And when they flow into a basin like the Dead Sea, the salts accumulate because they don't evaporate. Evaporation only brings the water up, leaving the salts behind, and over time, the salts begin to accumulate higher and higher. Let me give you an example. The Mississippi River carries about 500 million tons of rock to the ocean every year. About 300 million tons of this is in the form of solid sediment, but about 200 million tons is actually dissolved rock that exists as separate positive and negative ions in solution within the water. You can't see it in the water, but the atoms are all in there. When streams go into a closed basin, the water evaporates as fast or faster than it enters, and the salts accumulate. Normal ocean water contains about 3.5% salt as a percent of its total weight, mostly in the form of sodium chloride, table salt, but also salts of magnesium, sulfur, calcium, and potassium. Well, a place like the Dead Sea has, the water there is 31% salt. It's 9 times saltier than the ocean. In fact, the only place that we know of that's saltier is Lake Assal in Djibouti. Now, water can't get indefinitely salty. And the reason is that the dissolved minerals will begin to precipitate out at some point. And in other words, they actually will begin to form crystals of new rocks that occur when the water leaves that solution. You've seen that in daily life. If you leave water in a bowl for too long and that water evaporates out, it leaves a white powdery residue. Where does that residue come from? Well, the water that comes out of your tap isn't just water. It has all sorts of minerals dissolved in it, some from the ground, some from your pipes. You can't see it when it's dissolved in water, but remove the water and that, we call it a precipitate, the material, that powdery material that's left over begins to form. Well, if you have this occurring over geologic time in a basin, you can accumulate a tremendous amount of salt. Interesting, if you take an airplane and you fly across the western United States, places like Nevada and Wyoming, across the basin and range, you see something very interesting. You see whole sets of alternating mountain ridges. Remember these ranges of mountains from when the continent got pulled apart. But inside the basins, you often see white. And that white is salt that forms at the bottom of these basins from rainfall. There's not a lot of rain in these regions, and the temperature is quite high. So the rain that falls on the mountains dissolves salts out of the hills, washes them to the bottom of the basin, and then when the water evaporates off, it leaves that salt behind. These are called playas, and they can be quite large and develop large salt flats that can span quite large regions. Now, one of the largest regions of salt in North America is the Great Salt Lake of Utah. This is a huge closed basin that doesn't drain to the ocean, and salt has accumulated to very thick levels there. But interestingly, this didn't occur from a gradual process, just the continual cycle of rain washing salts out of the mountains. Within the state of Utah, back at the time of the end of the last ice age, Utah was covered with water. There were enormous inland seas there that were the result of that huge runoff of water from the melting of the glaciers. As those lakes evaporated away, because they don't drain to the ocean, the salts accumulated thick layers, the Bonneville Salt Flats, the Great Salt Lake. And you get these thick layers of remarkably flat salt extending for miles. In fact, these salt flats are so flat that they're actually used for testing rocket-powered cars. In other words, they're the best place on Earth where you can go for mile after mile on an area that's incredibly perfectly flat. There's one last reservoir that I haven't talked much about, and that's the deep Earth. Now, we know almost nothing about this. Either how much water is in the reservoir of the deep Earth or what its resonance time is. But we do know that not all subducted water comes back up at subduction zones. Some of it is trapped in the ocean crust and gets sent way down deep into the mantle. Now, this is actually work that I've done with my research group at Washington University, using a special type of seismic tomography that looks at the rate at which seismic energy gets damped out, that gets muffled as it moves through the Earth. This process, called seismic attenuation, is very sensitive to temperature, but it's also very sensitive to the amount of water that exists in the ground. And what we found is actually a huge region all above the Pacific Ring of Fire subduction zone, a region from about 700 kilometers down to about 1,400 kilometers that sits right on top of those subducted ocean plates. And this region has incredibly high attenuation, meaning the seismic waves from earthquakes lose their energy to friction very rapidly as they go through this whole ring sitting right on top of the old ancient subducted seafloor. And we've gone through a whole set of possibilities, and it's most likely due to water actually being pumped back down into the lower mantle. Now, even if that region contains only 0.1% of the rock as water, it would still have as much water as the Arctic Sea. And in fact, there's a region of the Earth called the transition zone that's from about 410 to about 660 kilometers down that geochemists have now figured out can hold as much as 2% of their mass as water. In other words, there could be 5 oceanfuls of water down in the upper mantle. It's quite possible that this water in the mantle, brought down by subduction, is what causes supercontinents to eventually split when that material rises back up. In other words, some of those hot spots that break apart supercontinents might actually be wet spots. It might be water brought down continuously by subduction, making the rock melt more easily and coming back up at the surface. It's possible that the very reason we have mantle convection and plate tectonics in the first place is because of having so much water in the mantle. See, we haven't really left Earth's interior yet. Even though water is the key agent of surface geology, it also plays an important role for the deep Earth as well. But you knew that already, because water, after all, was responsible for lowering the melting point of rock and allowing volcanoes to occur at subduction zones, creating much of the land that's created our continents. Oh, and water's important for one more thing as well. Of course, your body is 2/3 water, and our entire biosphere is based on water as well. But I'll be talking about that more later on. In the next lecture, I want to focus on the single largest reservoir of the hydrologic system, and that's the ocean.